solutions with incompatible data?
So let me start with the Navier-Stokes equations, and I would like to consider them in the zero viscosity limit, incompressible Navier-Stokes. So as you know, this is a quite important and challenging problem. So formally, one should have that the solutions of the Navier-Stokes equation should converge to the Euler solutions. This was proved by Swan more than 40 years ago in R3 with no boundaries. Then there is the result of Constantin and Hu for vortex patches. And there is also the theory of Diperna and Maida for approximate sequences of solutions with L1 LP control, vorticity control. So, but when there is a boundary, the problems presents additional difficulties. In fact, the problem becomes a singular perturbation problem, and from the physical point of view, the inertial forces, which are Laplacian, are not anymore negligible because they are able to stop the fluids, the fluid particles. So close to the boundary should be valid some kind. You cannot use Euler anymore, and then one should use something different, like for example the Prandtl equations that actually Prandtl introduced more than 110 years ago, introducing the very concept of boundary layer and introducing the rescale variable with the rescale with the square root of the viscosity. And away from the boundary, maybe Euler equation might be okay because you could neglect the viscous forces. So the conjecture could be that Navier-Stokes is some kind of superposition of the Euler solutions and Prandtl solution plus some correction term which should go like the square root of the viscosity. And that has been proved by, in 98, imposing analyticity on the data, both in the x, so in the tangential variables, and in the normal variable, both in y. And part of the difficulties in proving such a conjecture is that, as at the beginning, in the sense that it's hard to get good results for Prandtl solutions. And in fact, there are well-posedness evidences of the Prandtl equations by Girard-Varret-Norby and Girard-Varret-Nguyen quite recently. Other line of research to tackle the problem of the zero viscosity, they don't use, that do not take into account the Prandtl solutions, are based on the Navier boundary conditions. There you can see some of the papers appeared on this line of research. And I have to say that Navier boundary conditions have become recently more important because they, for example, for microfluidics, it has been shown that, or even nanofluidics, when you should use Boltzmann equation, you can still, in some cases, use the fluid dynamic equations as long as you use the appropriate boundary conditions. For example, Navier boundary conditions have been shown to be pretty good in simulating microfluids. Another line of research is flows with symmetries, in which the particular configuration of the flow makes negligible or make disappear the nonlinearities. And then there is the Cato type results, in which basically the idea is you get convergence as long as you control dissipation in a small layer of size nu rather than square root of nu. So this is an indication that maybe you can have well-posedness for Prandtl and still get, in some case, the convergence of Navier-Stokes to Euler. Okay, so I would like to consider the Navier-Stokes, besides the small viscosity, I would like to consider the case of incompatible data. So in which the initial datum at the boundary is, in general, is different from zero. So it's not well-prepared initial datum. There are many cases in the computational fluid dynamic community in which this kind of initial data, which are not well prepared, are simulated. The most important, I would say, is the impulsively started disk or cylinder, in which you have a disk which immersed in a fluid and in zero time passes from velocity 0 to velocity 1. So the disk is surrounded by fluid which has a non-zero velocity, but of course at the boundary the velocity is 0. Other configurations which are typical are flow configuration, vortex configurations, which are steady solutions of the Euler equation, in which you suddenly impose that they interact with a wall. And or said differently, if you, for example, if you move, if you are in the reference frame of the vortex, you can think of a wall which is impulsively started below the vortex. Okay, so what is the source of the difficulty when you have incompatible data? So think of the very simple example of the heat equation on 0, 1, just 1D, and you impose an initial condition which is 1, but you impose the boundary data to be 0 at the extreme. So in this case, you have the formation, an initial singularity, and you have the formation of sharp gradient around close to the corners. So in this case, in this very simple case, you can write the solution as a singular part, which has the form of an error function, and a regular part. And the derivative of the singular part is an error, so it behaves like a delta function. Let me mention the fact that recently there has been, by Jung and Temam, it has appeared this zero dissipation case in which they also do the boundary layer analysis, and recently Guo investigates the Stokes problem with incompatible data and a small viscosity. This is linear, though. So what happens in a nonlinear case? So you write the solution as a singular part plus a regular part. Then you plug, the singular part is an error function. Then you write the equation for the regular part. You invert the heat operator. And as a source, you see those terms, which is U singular times the X U singular. So you get a source term which is highly singular at the initial time, and which is might be a problem to deal with that, particularly when you would assume that the viscosity is small. There, in the slide is 1, but think of there to be an epsilon. And okay, so this problem of the non-well-prepared data has become an issue in the community of people who do simulations, because if you use spectral methods, you would immediately get deterioration of the accuracy of your solution. And for example, and the nonlinear viscous Barger equation has been recently investigated, and one of the bottom line is that, well, we use instead of usual spectral, we use spectral finite element methods. So because they derive from a weak formulation of the equation, so they are more tolerant. They should be more tolerant to the singularity, to the initial singularity. Okay, so let's go back to the Navier-Stokes solution, our problem, and what I would like. Well, I will show these slides over and over. What we would like to prove is that the Navier-Stokes solution can be written as a Euler part plus a Prandtl part plus correction, which are as correction to the Euler flow plus a correction to the boundary layer flow plus an overall correction. So this is the thing which you would like to prove. And the main assumption we will do, which is a strong assumption, is the analyticity in the tangential variable. So let's start from the Euler equation, and we will assume that. So what does it mean, analyticity assumption? Well, we will assume that the initial datum with respect to the tangential variable is analytic in a strip of the complex plane, and the norm, which so in the right below corner, the norm is expressed in terms of the Fourier transform, and it is weighted by an exponential function, and that row over there tells the analyticity radius. So this is the basic. So more formally, a function which depends just on the tangential variable, the norm is as m and rho. So m is a sort of Sobolev exponent, and then there is the exponential part. Of course, I mean, the polynomial in C is just there for convenience. I mean, but that's it's easier to make computation if we keep the Sobolev polynomial there. And if a function depends on x and t also on time, we will allow the radius of analyticity to vary with time. So the rho depends explicitly on t. And we will see in a moment why. And instead of the normal variable, the one which is perpendicular to the boundary, it's L2 plus and derivatives are considered to be L2. Okay, so this is all. So let's go. So for Euler equation, it's possible to prove is that if initial datum is analytic with respect to the tangential variable, and L2 with a sufficient number of derivative with respect to the normal variable, initially it's incompressible, and initially it is zero flux at the boundary. Then up to a time t which can depend on the size of the initial datum, there exists a unique solution which preserves analyticity. And but with the radius of analyticity which is shrinking. And the proof, it's just a rephrasing of the ideas appeared in Foyash and Teman, Ferrari and TT, and Levermore, Oliver, and Kukavica and Bicol. And it's a very nice idea. And I think that the easiest way to see it is just to show a line which appears in the paper of Levermore, Oliver in the vorticity formulation. So one defines that analytic semi-norms, and so A of R is just the derivative. And if you do energy estimate for that analytic semi-norm, you get this inequality in which the first term on the right-hand side is a bad guy, is a bad term, but that can be killed basically choosing the row to satisfy a differential inequality. So, for example, if rho dot plus rho C1 and so on is lesser than 0, so the bad term can be cancelled. And then you get, using Gromwell, that the analytic semi-norm is bounded in terms of the initial data and in terms of this integral of theta, which is just the Sobolev norm. So as long as you have the regularity for the Euler solution in Sobolev space, you get analyticity. So this is, I would say, it's classical now. So having constructed the Euler, the other thing which I should say is that there is interest in the estimating on how the radius of analyticity shrinks. For example, the paper of Kukavica and Bicol, they were able to recover the estimate the rate of decay that was in the paper of Bardosh of Benanchour of 1997. Instead, this technique, which is due to Levermer-Oliver, you get worst estimate. So having constructed the Euler solution, we pass to the Prandtl solution. And so these are the equations that they are an asymptotic approximation of the Navier-Stokes equation derived by Prandtl. And we have here, this is also, it's incompatible. So that's here that there is the incompatibility, because the U, capital U there, which is the initial, which is the boundary datum, is not, does not satisfy, is not zero initially, because it derives from the Euler solution. So here, what we did in a paper appeared in recently in 2013 on nonlinearity, we decomposed the Prandtl solution as a singular part plus a regular part, UD is regular, plus W, which is just takes into account the interaction between the regular part and the singular part. So the singular part, it can be written explicitly. It's here. It's just an error function, as said several times. And it does have a corner singularity. The regular part satisfies a Prandtl equation, which with the analyticity hypothesis can be solved using, the results appeared several times in the literature. And then there is this interaction part, which can be recast. So think of it in terms of the heat equation, in which the nonlinearities are at the right-hand side. And, well, let's forget about the nonlinearity. I would just like to focus on the singular part. So this G naught, in which, is there a pointer here? Is there a way to point? Oh, this one, okay. So here we have the product of the singular part. So the one for the Barger equation are a problem. So what happens here is that, okay, let me just say that we recast, inverting the heat operator, we recast it in the form like that, like U plus an operator of F. And suppose that the operator F satisfies this quasi-contractility hypothesis in the sense that you estimate, so we are in a Banach scale. And so we estimate the norm of the difference of FW1, FW2 in a space which is as a less strong norm, and you can estimate in terms of the argument on a stronger norm, paying the price of this denominator, plus a mild singularity in time. So then in this case, you have a unique solution, but with in a space which becomes weaker and weaker with time. And the proof is just due to an old idea of Nuremberg, in which you define the Banach space, in which you weight the norm with the function of time, which becomes smaller and smaller with time. And so in this auxiliary Banach space, you can prove that the operator is contractive as long as the beta, the times, the speed at which you get the deterioration of the norm is big enough. So the idea of applying this idea to the how do we apply it to the Prandtl equation? So we set up function spaces in which you have analyticity. So the index of the Banach scale is the radius of analyticity. Alpha is the rate of exponential decay to infinity, and beta is the speed at which the analyticity radius shrinks. So the other difficulty is the appearance in the source time of the singular part. And basically, what helps is the particular structure of the equation is the fact that the singular part applies multiplied always by a function which vanishes at the boundary. So let me just say it very sketchy way. So this is the nonlinear structure. And so you see that when there is the derivative which creates the delta function, there is the velocity at the boundary which is 0. So this is basically what allows, in this case, to overcome the difficulty of the incompatibility of the data. So, okay, so you invert the heat operator, and in our space we have two derivatives with respect to time. So let me just, so you have, okay, so this is very technical, but the point is that you have three derivatives with respect to the normal variable. One, you plug it into the heat kernel, so you get a singular part which is t minus s square root, but it is integrable. And when you get the two derivatives you get the derivative of delta function. But when it's multiplied by the normal velocity, it goes to 0. So you get a singular behavior, but it is integrable. So at the end, you get two singularities in time, which are separated, and they are both integrable. So that's just as simple as that. So the theorem is that so the Prandtl equation can be written in terms of a singular part plus a regular part, which, okay, I already discussed that. So concerning the Prandtl equation, there is also, let me just mention the results of well-posedness due to Olienic and all that came after, in which there is imposed monotonicity of the flow, which are hypotheses that allows, avoid the separation of the flow, the formation of the recirculation region. Then there is a whole bunch of results which use analyticity. And then there is the recent result of Gerard-Bardet and Masboudi, in which they get better than analyticity because they do in the Gevrey class, but they have to impose something which resembles the monotonicity hypothesis of Olienic, but much weaker though. And then concerning the justification of the boundary layer, there is the negative result of Grenier, Gouin, and Guyen, in which they show that in Sobolev spaces, the asymptotic expansion that I showed you could break up in time 0, basically. So I already discussed the ill-posedness result. Just let me mention a little bit about the fact that Prandtl equation admits a singularity, a finite time singularity. And we did some numerical exploration of that. And so this is, we did some comparison between Prandtl and Navier-Stokes. So in Prandtl, what happens is, what leads to the singularity is the formation of a recirculation region. And the structure of the equation is very rigid. So when the formation of this kind of backflow, there is nothing which can oppose to the formation of backflow. And then at a certain time, you have the eruption of the flow and a sudden appearance of a singularity. Well, in the Navier-Stokes at high like 10 to the 5, 10 to the 4, there is a response of the outer flow to the formation of the recirculation region. So what one can say that when in Navier-Stokes, there are three stages, in which the first stage there is no interaction between the outer flow and the boundary layer, and then Prandtl equations are fine. So there is a good agreement between Prandtl and Navier-Stokes. A second stage is when you have a large-scale interaction, so the outer flow acts on the boundary layer, and then you can see some kind of discrepancy between the boundary layer of Navier-Stokes and the boundary layer predicted by Prandtl equation. These discrepancies are, however, purely quantitative, and there is no appearance of high gradients, which can be reminiscent of the Prandtl singularity. And then there is a small-scale interaction in which there appear several critical points of the pressure gradient at the wall, and there is a formation of cascade of recirculation region, formation of spikes and high gradients. And this has been, okay. So these are kind of a picture of what happens at the 10 to the 4 Reynolds in the Navier-Stokes solution. And this kind of formation or cascade of vortices. Okay, so this picture are basically shown to show that that the pressure, that the vorticity at the boundary is a good diagnostic to understand what happens inside the flow. So what we ask is that comparing Navier-Stokes to Prandtl, I mean, Prandtl has a singularity. So you can follow the singularity in the complex plane before it hits the real axis and leads to the blow-up of the flow. So, the question we asked, do Navier-Stokes have complex singularities? And if the answer is yes, how do they compare with the Prandtl singularity? So what we show that Navier-Stokes for the impulsively started disk do have complex singularities, and actually have three complex singularities. One is the Prandtl singularity, clearly identifiable as something as a Prandtl singularity. And then there is another singularity, which is a so-called large-scale singularity, which is related to the interaction of the boundary layer with the outer flow. And then there is another singularity, the one which gets closer to the real axis, with a scaling which goes like 1 over Reynolds, which is the small-scale singularity. So one of the conclusions is that the Prandtl singularity has nothing to do, contrary to what it was believed, to the separation phenomena in Navier-Stokes flow. So the phenomenology leading to the Navier-Stokes separation seems to be different from what happens to the Prandtl equation. So let's go back to our asymptotic expansion. So we are here, and then we want to construct the first-order Euler correction. So I just show you the equation, which is just linear. So in which there is the Euler, first-order Euler, which interacts with just with the Euler. And this is introduced to cancel the flow generated by Prandtl. So basically what happens is that Euler generates slip, tangential slip. Prandtl is introduced to cancel this tangential slip. First-order Euler is introduced to cancel the normal flow generated by Prandtl, and so on. And at a certain point, of course, you have to close, allowing this equation to cancel everything. Okay, so this equation clearly presents no problem, so I think we can assume that this equation allows a solution, as a solution. So also the first-order correction for the Prandtl equation can be chosen to satisfy a linear equation. So for this part we are okay. So let's go to finally to the overall correction, which satisfies this kind of equation. And F is a very cumbersome term which takes into account all the interaction between all the boundary layer and outer flow. Okay, so we simplify this equation as a source term, and it has flow, that it has a boundary condition. So we can cancel the boundary condition with solving this problem. So in the end, we have to solve an equation which is Navier-Stokes type, which just is homogeneous everything except the source. So the functional setting is similar to what I showed you before, except that now we take just two derivatives with respect to the tangential variable, and it is L2 with respect to the scaled variable. And the analyticity, the analytic norm in the tangential value is the same. So to solve this problem, okay, we just want to use the Kato-Fujita formalism. So we first tackle the problem of solving the linear Stokes problem, And this can be accomplished quite simply. First, when you introduce the appropriate Gaussian kernel, then you introduce the convolution with the odd extension. So this operator E solves inverts this part here and has 0 data, boundary data. The third step is projection, because we want it to be incompressible. Then this generates boundary data. So we introduce the Stokes operator that solves Stokes equation with source term. And then this is the operator. So it's PE minus this part here that cancel the data. So this this is just formal, but it can be written quite explicitly in terms of Fourier transform and so on. Very much like the Ukai formula. So this operator solves this equation. And so having to solve this one can recast this equation in this operator formula where the Stokes operator acts on the linear part and then the weakly nonlinear part, and there is source. And one can prove, I'm skipping all the detail, one can prove that this should be G, that this operator satisfies the quasi-contractiveness hypothesis, so that it's contractive in the appropriate Banach space. So the conclusion is that we have proved this theorem that under the hypothesis of analyticity in the tangential direction, the Navier-Stokes solution is Euler basically away from boundaries and Prandtl close to the boundaries. And this has been proven rigorously justifying this kind of expansion. Just a final comment on that is that this correction depends on the fast variables. So it's the variable that Prandtl used inside the boundary layer, but it is everywhere. So also inside the flow, this expansion says that there is some small thing that varies rapidly with a normal variable. Maybe this is unsatisfactory. However, one could just point out that this expansion could be taken up to the second order. So in the sense that these Euler part are just Euler, Prandtl is just boundary layer, and this one it can be made, the overall correction can be made smaller. So epsilon square and so on. And so I thank you for your attention.